We just looked at a series of rules that tell us how electrons are arranged within orbitals in an atom. Those rules were the Aufbau principle, saying that we're going to fill orbitals from the lowest energy and build up. The second was the Pauli exclusion principle, which says that no two electrons can have the same 4 quantum numbers, and as a consequence of that, we can have no more than 2 electrons in an orbital, and those electrons must have opposite spin. And the final one was Hund's rule, which says that we will fill degenerate orbitals singly, that is with a single electron, before we pair electrons. Now there are a couple exceptions to this rule, and specifically we're talking the chromium group and the copper group on the periodic table. And for the purposes in this course, I only want you to be aware of 2 exceptions for 2 specific elements, and that is for chromium and copper. Once we get down to lower rows within that so-called D block of the periodic table, we start to see more and more exceptions. So we're going to limit it to those 2, chromium and copper. So let's look at those configurations and figure out why they might be exceptions to these rules. So if we remember our filling order, we can write this out: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4f. All right? And we are going to fill them in order along these diagonals if we go across as such. So we can start by placing my 1s orbital at the low energy, followed by 2s, followed by the 2p. There are 3 of those, remember. M sub L values, -1, 0, and -1, tell me that there are 3 different orientations for this p orbital in space. Then we'll go up to the 3s, 3p. The 4s then starts to overlap. And then we go back to 3d, 5 of those, and then the 4p, 3 of those. So how many electrons does chromium have? Turns out, if we find it on the periodic table, it would have 24 electrons in its neutral ground state. So we would start filling according to the Aufbau principle, starting at the bottom up, and following the Pauli exclusion principle, opposite spins, no more than 2 electrons. So 1, 2, 3, 4. Then Hund's rule tells me that I would place electrons singly before pairing them. So that's 7, 8, 9, 10, 11, 12. When we get to degenerate orbitals like this, and we just went through the 2p series, I can actually put electrons anywhere in these orbitals. Because they are all the same energy, it doesn't matter where I put them. So this could be 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now we have the electron configuration. What we actually see, though, is this 4s electron gets promoted to the 3d shell. Now we have something that looks like this. And so why would that electron want to leave this 4s orbital, which is of lower energy, and go to a slightly higher energy in the 3d orbital? Well, it turns out that there is an extra added stability with these so-called half-filled subshells. So the 3d and the 4s both are now half-filled. So what this does is it evenly distributes the charge about that atom. We have this spherical charge distribution, and we've minimized the electron-electron repulsion that was occurring in the 4s orbital. And so that's the driving force for this arrangement of electrons. And this difference here, this energy gap between the 4s and the 3d is very, very small. So it doesn't take much for that to be promoted, and that cost is less than the spin pairing cost that we saw when they were paired in the 4s orbital. We can write out the electron configuration in our text format: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. 5 electrons in that d shell. We can also write this with our abbreviated notation or our noble gas notation, and this would be noble gas of argon. It's the previous noble gas, and those electrons that are part of that noble gas configuration are those that I boxed here. And then we have 4s1, 3d5. Now let's look at copper. Copper is that second exception that I want you to know. Can you tell me how many electrons copper has? Copper has 29 electrons. We'll fill from the bottom up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Whoops. They all have to be the same spin. 25, 26, 27, 28, 29. We get this arrangement. Again, we see a promotion of this 4s electron to that 3d shell. So what does that look like? Now we have the filled 3d shell. And for the same reasons that chromium was an exception, copper is an exception as well. Except instead of talking about half-filled subshells, we're talking about a filled subshell. So there's added stability again with a full subshell of electrons. So we have this even spherical distribution of charge. If we were going to write the abbreviated electron configuration for this, we would have the noble gas configuration of argon gets us up through the 3p, and then we'd have 4s1, 3d10. These two elements are the only exceptions that you need to be familiar with when it comes to filling electrons in these orbital energy diagrams. We will come back to this idea of the added stability with half-filled and filled subshells when we look at some periodic trends. Thanks for watching.